Hello everyone, this is Lab 5, Physics 2211, and I'm Ben Zhang. Here I'm going to give a brief introduction and an overview of what's going to happen during this lab. The purpose of this lab is to track a spring's motion. We're going to do this by using the video given online and using the tracker app to observe their motion. Here are some important formulas for this lab. The first formula connects the stiffness of a spring, K, to the oscillation behavior of a mass on it. M is the mass attached to the spring, and omega is the angular frequency of its oscillation. A stiffer spring results in a faster oscillation, giving a larger W, or omega. If you know this period, you can calculate omega equals 2 pi over t, omega equals, and then calculate k. This is derived from the standard simple harmonic motion differential equation. Angular frequency describes how fast the system oscillates in radians per second. One full oscillation corresponds to 2 pi radians. A shorter period means a larger omega. You can measure the period from data using zero crossing or peak spacing. L naught is the natural unstretched length of a spring. L is the current length of the spring. The expression L minus L naught gives the actual stretch or compression force. Here are some fundamental principles of this lab. The first principle tells us how force creates motion. When we attach a mass to a spring, the spring force is what accelerates the mass. When we plug that into Newton's second law, we get Mf equals ma, or ma equals kx ma. This equation explains why an object speeds up when it's far from equilibrium and slows down when it approaches it. The spring's force and mass's inertia work together to produce oscillations. Without Newton's second law, we couldn't predict how quickly the mass changes direction or how fast the motion happens. The principle says that whenever you apply a force on an object, it pushes back the same force in an opposite direction. When you stretch a spring, you pull on the string, and the string pulls back on you with equal strength. That is Newton's third law, the equal and opposite spring force. The system in this lab is the spring and the earth, and the surroundings would be nothing. Here's the video that I used.
Today I'm at the University of Sydney talking to Rod Cross, who's done physics for
top end, let the bottom end go so the slinky stretches.
and it dangles freely.
And I'm going to ask the question, what happens?
This video is from Vertasium. I don't know if I'm pronouncing that right, but this is not my video. Using the video shown above, I was able to use Tracker to track their positions. The top plot shows X position versus time. This horizontal motion is small and steady, but has some errors which can be explained in the next slide. The bottom plot shows Y position versus time. The mass moves steadily downward, with the drop becoming faster after 2 seconds, suggesting increased stretch or increased gravity. Acceleration. Overall, the motion is mainly vertical, as the spring acts it drops down from the rest position held by the professor. In this lab, the main sources of error are human error because there aren't many other factors other than me clicking the tracker and then inputting the tracker data into the code. So most of the errors would probably be from me. So these are just some questions for the lab. The first question would be, what physical factors do you think determines how fast a spring oscillates the mass, the spring constant, or both? And the answer would be that a stiffer spring, resulting in a larger K, oscillates faster. And then a spring with a larger mass oscillates slower. The second question would be, based on the motion I saw in between the graphs, does the spring restoring force always point in the same direction as the motion? And the answer would be no. The restoring force always points towards the equilibrium and not necessarily in the direction the mass is moving. Sometimes the mass is moving away from the equilibrium due to inertia while the force is already pulling it back. This opposition between force and motion is what creates oscillations. Thank you for listening.